Hello friends, today we will discuss a very important topic, and that is subsurface drainage system in a road. Highway drainage is extremely important in pavement design as well as in construction, and road will develop cracks, potholes and other failure, premature distresses if proper drainage is not provided, and that will certainly affect the riding quality and strength of the pavement. A poorly drained pavement is twice as costly as a well-drained pavement. An efficient drainage system will enhance the life of the pavement. It will facilitate free flow of traffic, reduce maintenance cost, and will perform better. Water can enter a pavement or soil subgrade from different sources. It can be because of seepage of water into the subgrade from higher ground level to the lower ground level. It can be in transverse direction or as well as from longitudinal direction. Or maybe because of rise and fall in the level of water table, which generally happens because of rains or before monsoon and after monsoon. Percolation of water through surface of the road. Maybe if you have earthen shoulders and ponding of water happens on the shoulder, then that water can also percolate in different layers of the pavement. It can be through transfer of moisture from the median in case of multi-lane highways. If proper care is not taken, then in that case, water can enter different layers of pavement from the median also. Or it can be because of movement of moisture from lower to upper or from upper to lower layer of the pavement or the soil layers. Or it can be because of water vapor, movement of water vapor through the soil. The presence of water in any layer of the pavement will create the problem of stability. If soil subgrade gets saturated, the strength will reduce. Now, some materials like sand or gravel, they are free draining materials and they do not generally pose the problem of drainage in a layer. But clay soils are difficult to drain and they have water retention property. And therefore, base and subbase material can be designed using free draining materials so that water entering into these layers can be drained quickly without any problem. But the problem occurs when the subgrade is made of clay soil or pavement is constructed in marshy areas. In such situation, it becomes necessary to provide subsurface drainage system in the pavement. And these systems are provided where ground table is likely to rise to a level within 1.2 meter of the subgrade level. Or subgrade is highly impervious like clay, or there are chances of water seepage from side slope or from hillside to the pavement layers, or frost action. Frost action is likely in subgrade beneath the pavement, or there is a possibility of rise of water through capillary action. Now, I'll discuss in this session 3-4 types of surface drainage system, and the first is lowering the water table. If water table is high, then in that case, let us say this is the pavement and water table here, this is the position of water table. Water table. Now, what is done here that on each side of the pavement, we provide a trench, and within this trench, you provide the filter material, and here a perforated pipe on either side. These are longitudinal drains. Longitudinal drains. Now, this is a perforated pipe. It can be vitrified clay pipe also. It can be a metal pipe also. Now plastic pipes are also available. But perforated pipe is preferred because of their longer life. And here in this trench, we provide the filter material. Now I'll tell you a little later what is the filter material. Here we provide the filter material. This is the filter material. And here at the top of this, we provide some cap of impervious material like clay, so that water does not enter or it does not clog the top of the drain. So you have a vertical drain here, vertical filter material, and below that you have a perforated pipe in longitudinal direction along the road. And the depth of this drain or filter material, it will depend upon where do you want to have the water table after provision of this drain. So after provision of this drain, the water table will be here. This will be the water table after provision of drain. Now this system does not work when the subgrade is of fine grained material. When subgrade is made of fine grained material like clay. In that case, in addition to these longitudinal drains, we also provide transverse drains like this. We also provide the drains in the transverse direction below the pavement. The plan of this will be, this is the longitudinal drain, and here you provide the transverse drains. Now this is the ground line of the pavement. So we provide these drains, and these are staggered generally at 60 degrees centigrade and all along the length of the pavement. So water will drain from these transverse drains to the longitudinal drain, and these longitudinal drains finally will drain the water into the natural river or natural drain. So this is the combination of longitudinal and transverse drains. The second is capillary seepage flow. This is generally a problem when you construct a road in hills by cutting the slope in the vertical direction. Now this is the cut slope. Here we provide the drain for the pavement, and that is the pavement. Let us say this is the pavement structure. These drains, to check the seepage water entering into the pavement, they are provided well beyond the drain or well beyond the pavement. Here for example, the provision is same, that you provide a perforated pipe here and a filter material in this vertical trench, and then seal it through some impervious material like clay. But purpose is different. Purpose is to control the seepage of water from this up slope towards the pavement. So all water will be captured by this filter material, and then it will be collected in the pipe, and this pipe will drain the water into natural drain. So there will be seepage water here, there will be no seepage. No seepage on this side. So pavement is protected. Third is control of capillary rise. When it is suspected that water can rise because of capillary action and enter into subgrade, then it is required to control this capillary rise by providing a blanket layer in the pavement, or it can be a bituminous primer, or it can be simply a layer of geotextile. So here we provide a layer of sand, or you can say blanket material, or it may be bituminous primer, or it can be a geofabric like geotextile. Now this is the water table, natural water table. This is the level of, let us say, water table. This should be at least 15 centimeter, and this depth should be minimum 60 centimeter. That is the criteria. Where should you place this layer of geotextile or the sand blanket? That is 60 centimeter below the pavement and at least 15 centimeter above water table. So these are the methods to control the moisture or to stop the moisture entering into different layers of a pavement or in subgrade soil. Now in all these cases I told you about the filter material. So what is the filter material? Now design of filter material is equally important for the success of drainage layer. So basic consideration is that this filter material should be coarse enough so that it does not migrate into the soil, subgrade soil or drainage layer, into the pipe also. At the same time, it should be fine enough so that the subgrade particles, soil particles, do not migrate into the filter material. These two requirements are there. And to satisfy these requirements, D15 of filter material divided by D15 of subgrade soil should be larger than or equal to 5. That is the permeability criteria, permeability ratio. Permeability ratio. And second criteria is what is called the piping ratio. Piping ratio says that D15 of filter material divided by D85 of subgrade should be less than 5. That means if you know the grain size distribution of subgrade soil, this is the size, sieve size, and this is the percent passing, 0 to 100. So if this is the gradation of, let us say, subgrade soil, so D15 of filter material, that is the D15 size. D15 is the sieve size where 15% of the soil will pass. This is the D15 size. This should be, D15 for filter should be more than or equal to 5 times D15 of subgrade soil. So 5 times is here. Okay, this is, let us say, 5 times size. 5 times D15. And D15 of filter size should be less than 5 times D85 of subgrade soil. Now let us say D85 is this size. So this is 85% here and this is a D85 size. This size, D85. Now take 5 times of this. Let us say this size here. 5 into D85. What this equation says that D15 filter should be less than 5 times this. So your filter size should be within this range. Less than that, more than that. So D15 filter size should be within this range. Another criteria is that this filter material should not penetrate or migrate into the perforated pipe. And therefore, the D85 size of filter material should be equal to or more than 2 times dia of the perforation. Dia of perforation in the pipe. So here you can put a point here that D85 should be 2 times. Let us say if you have 10 millimeter diameter of the perforation, then 20 millimeter. So D85 will be here. Should be more than this side. Right. So any line here, if you draw any curve here, which is beyond this and within this, that is basically your filter material, design of filter material. Let me just explain it further with the help of one example. And the grain size distribution of subgrade soil is given like this. 1.18 millimeter passes 100%, 0.425 millimeter, that is 425 micron, 93%, 0.3, 85%, 150 micron, let us say 60%, 75, 0.075, 15%, 0.53, 0.053, it is 7%. Now, this is the grain size distribution of this curve, the distribution of the subgrade soil. Percent passes 0 to 100, 100. This size is 1.18, and you have, let us say this is 0.001, this is 0.01, this is 0.1, this is 1.0, 2, not 2, 10, 20 millimeter. This is the size in millimeter and the percent passing. So what it says that 85% size is 0.3 millimeter. Okay, so you can find out, if it is not given here, you can find out from this graph. Now this is the 85% and this size is 0.3. This size is here. This is 0.3 and that is D85 of the soil. D50, 0.075. This is 0.075, let us say 15%, and this is your size 0.075. The first condition of permeability ratio is that D15 of filter material should be more than or equal to 5 times D15 of subgrade soil. And D15 of subgrade soil is 0.075. So let us say 0.375 millimeter. And second condition is that this D15 of filter material should be less than 5 times D85 of the subgrade soil, and that is 0.3. So this is 1.5 millimeter. So 0.375 is here and 1.5 is here. Let us say here 1.5. So this is 1.5, this is 0.375 sieve size. So D15 for filter material should be within this range. Within this range. And let us say the diameter of perforation in the pipe is 10 millimeter, and therefore D85 of filter material should be twice or more than 2 times this diameter, and that is 20 millimeter. 20 millimeter is here. So this is the point. Let us say this point is A. This point is A here, corresponding to D15. This point is B, corresponding to D15, and this point is C. So any material which will satisfy this condition of gradation, which is D85 beyond this and 15 between this, that could be the gradation of the filter material. That is how we design the filter material for subsurface drainage system. So friends, thank you very much for watching this video. If you have any question, you can write in the comment box.